Hi everybody, welcome to the first video in this unit. It's on integration, the Riemann sums and definite integrals. You can see the objectives written here. Also, here's a lovely picture of Bernhard Riemann, taken in 1863. Kind of a fetching looking guy here. And so let's get started. So in class I talked to you about how these two areas of calculus interact together. We talked about instantaneous rate of change, which led to the slopes of tangents, which led to derivatives and differential calculus. Then accumulation of changes over time led to area under a curve, which led to the integral and integral calculus. So you can see here a little demonstration of here's the derivative. If you take the derivative, it's 2x. If you take the integral, you end up back at the function. And so notice here that the integral without the plus c could, or with the plus c, could lead to many different derivatives. So once again, in the exercise that we did previously, we looked at 4 methods of finding the area under a curve. And we talked about the left method, the right, the midpoint, and trapezoids, dividing things into trapezoids. And I don't have trapezoids listed here, but you can kind of see here you have one that would be a left side sum in the green, and then this yellow one would be a slightly different from the right side with a wider, and you can see that it would be a little more accurate the more rectangles you have. You can see here big chunky rectangles, right? They don't have to be above, just above the x-axis. They can be below. You can have negative area. And then you can see what that same function looks like if you use multiple more than one. So I would much rather do this one by hand, but with calculus we can handle this one. So once again, finding the area under a curve means that you're going to have to limit what part of the curve you're finding the area under. So on this particular diagram you can see we've got this lovely curve, and we're going to limit finding the area under the curve from A to B. And so dividing those up into equal parts, we call these parts partitions. And a lot of times they'll use this delta x to describe the length or the width then of each of the rectangles that you're using under here. So say for instance, I have A to B, and I want to know how to divide those partitions up so that they're equal widths. We said in ours that we just picked half because that seemed a very convenient thing to do. Well, you can do that for any length, and one way to find the width of the partition would be delta x would be equal to b minus a over the number of partitions that you wanted to find. So say for instance this is 20 and this is 5, then you would have 20 minus 5 over, and let's say I wanted to do 10 partitions. So that would be 15 over 10, or each one would be 1.5 wide. And so that's just as easy as you could possibly imagine to make those all even, okay? And so finding the area under the curve means dividing the area under the curve into partitions of equal length, even when it's not always feasible, okay? And so to do this by hand, what we did is we found the area under the curve to be the addition of the areas of the rectangles that we divided this piece into. But we could take that a little further. We could use notation that said the area would be about the sum, remember the summation, of the areas of rectangle. Areas of the rectangles, using the summation notation. And we could say the same thing. We could say that the area is equal to the sum of the area. Well, area is just height times width, right? That's how you find the area of a rectangle. All right, so then we could take that just a little bit further, and we could say that the area was equal to the sum of the heights. Well, remember that the heights were all the y values. So f of x times then the width. Well, the width is each width here, and the ones that we did in class were 1/2, but here the width would be delta x. Okay, so then if we take that a little bit further, we would say that the number of partitions, like say we wanted to do the sum of, let's say 1 to infinity, We want to do an infinite number of rectangles to divide that area of height, f of x, and width of delta x, right? If we do that, and then we take the limit of that as n approaches infinity, right? Then we end up with the area being the integral from a to b, just like that, of f of x delta x. We change that to dx, right, in our integral notation. And that would be the area under the curve. So this would be a definite limit instead of indefinite. So no plus c, definite limit. Okay, I'm sorry, definite integral, not limit, definite integral. So this a down here, this a would be the lower limit, like the a over here, and then this is the upper limit. All right, so this is a lot of theory, but basically we're getting to the point where we want to be able to use calculus to find the area under the curve instead of having to divide it up into rectangles or use some kind of method to do that. So in this video, I really wanted to go over a lot of the calculus notation so that you're not surprised by it. You've been taking the integrals, but maybe you didn't exactly know what all of the symbols meant. So let's start with this integral symbol right here. It's in the shape almost of an S, right? Because for summation, and we saw that the sum of the areas underneath. The blue is the function that we want to integrate, and then dx are the slices along the x. They were the width of the rectangles, okay? So if we add to this function that we want to integrate is called the integrand. Integrand. And then this x right here is the variable of integration. Integration. Okay, and so this is the one that we've used to. Now, the one on the previous screen said a to b, right? So the b is the upper limit, and the a is the lower limit. So what you would say is this is the integral of f, the function f of x, right? If you had something that looked like this, a to b. So this is the function, the integral of f of x from a to b, so lower to upper. Okay, so the theorem says if a function f is continuous on the closed interval from a to b, that same closed interval, then f is integrable on ab. That is that if I have the integration from a to b of f of x dx, it has to exist. And that's what that means. That is, this exists. So here's just a quick illustration about what we're trying to find. So if we're using the indefinite, if we're using an indefinite integral, we're talking about the area under a curve in any part of the curve, right? Not a specific part of the curve, but anywhere on that curve. But a definite integral, which adds that a and b to it, we're actually trying to find it between a and b. On the ones that we did in class, we did from 0 to 2, or 0 to 2.5. So we were finding the integral from 0 to 2.5 of that function, 2.5, of the function, right? And so when we came up with an average, we were approximating it, but this is what we were actually trying to do. So there are a few more properties of integral notation that I want to go over in this video. And the first one is the reversing the interval. All right, so it says reversing the direction of the interval gives the negative of the original direction. So notice here that this is a to b, but over here it's b to a, right? Do you see them flipped? So what that does is it just makes that whole integral, that number that we get, negative. So write that down. Reversing the direction of the interval gives the negative of the original direction. Okay? The next one is the interval of zero length. And what I want you to notice is that we're taking the integral from a to a. Look here. There is no area. So any time, like say for instance, I wanted to take the integral from 3 to 3 of f of x dx, that would just be 0. Okay? And just like we would say here, we would say that the integral from 1, or let's say 0 to 2 of f of x dx would be equal to negative the interval of 2 to 0, because you're going the opposite direction, f of x dx. So one more property is that we can also add two adjacent intervals together. So for instance, a to b would be from here to here, right? And so what that would be the integration of a to c plus c to b. And it would be in that order because c is going to be the lower limit. So adding those intervals together is going to actually allow you to go from A to B. All right, so for instance, if I had from 1 to 5, let's say 1 to 5, 1 to 5, I want you to be able to see it, 1 to 5 of f of x dx, that's going to be equal to 1 to 3 f of x dx plus 3 to 5 f of x dx. So you could split them up. And so you could find this integral plus this integral, and it would equal the whole thing. All right? So we're going to do a lot of these on Monday using this notation, but I wanted to kind of put all of it together. So I hope you took good notes, and I will see you in class.